So next, I'm going to give you Professor Michael Balogh, who's an associate professor in physics and astronomy in our department. He specializes in the star formation in groups of galaxies, properties of intergalactic hot plasma, formation of galaxies, and all sorts of cool astronomy that he may not tell you about, but you can certainly ask him about during the rest of tonight. Thank you.
OK, well, thank you very much. Right, so, and you'll notice, so thanks very much for the introduction. You'll notice on the list of things that I'm supposedly an expert on, meteor showers and comets were not one of them. And that's what I'm going to talk to you about today. I want to start, before I give the lecture properly, with just a little tour of what we might see in the night sky if we get outside and the clouds part their way for us, just so you are sort of oriented of where might be interesting places to look. Especially before the moon rises. So this is looking towards the east. Okay, as we go out onto the field, this is set for the time just before the moon is going to rise. Okay, and this is important because once the moon rises, the sky is going to get quite bright and it gets harder to see faint objects. The main event that we're looking for today are the Perseid meteor shower, and when we can see those well, the meteors will all be flying over our head, and they seem to originate from a point which, on this slide, is sort of just above that building, which is not a real building on this campus. Okay, this is a fake landscape. But if we look sort of towards the north of east, just rising above the horizon is the constellation of Perseus. Okay. You can find it. So I'm not very good at my constellations. I don't actually know constellations that well. I know about 3 of them, and one of them is Cassiopeia, which is that W-shaped constellation of bright stars up there. This is the best way I can get my constellations, is to label them on the sky. Okay, and that's Cassiopeia up there. You can pretty easily pick it out as a W in the sky. And if we follow that down towards the horizon, you can see the constellation of Perseus. And that's where the Perseid meteors originate from. Okay, and they'll fly from there. But the moon is going to rise in the east just shortly after 10 o'clock. Okay, and that will make it the sky quite bright in this direction. There's no need to look directly at Perseus to see the Perseid meteors because they fly right over the sky. So the best thing to do is to look at a dark region of sky. If you can look where the sky is dark and let your eyes adjust, then you can see fainter objects and therefore more meteors. So if we scroll over towards the west, looking away from the moon, we're looking out over Columbia Lake. That's probably your best place to be training your eyes. So if we look towards the west, might be a good place to look. And the other advantage just here about 10 o'clock before the moon rises, in addition to various stars, we see a couple of bright objects over here. Okay, those are not stars. And if we, again, just label them on here, those are actually planets. That's the planet Saturn and the planet Mars. Okay, and they should be, as long as there's no clouds there, quite bright objects just above the horizon towards the west. But they will be starting to set by about 10 o'clock, and so we'll lose those. So if you want to see something, and I'm not sure if there's going to be any telescopes set up on the field. Unfortunately, because of the date change, a lot of and the bad weather, we may not have any telescopes set up on the field. If there are, they may likely be trained on Saturn and Mars, and you can get a nice look at one of those towards the west. So that's just to orient you a little bit. Now I want to just talk about a few random astronomy things. Okay, so I'm going to talk about these things that I'm not an expert in. Meteors, supermoons, and comets. Okay, and I want to say a little bit about why these things are all related to one another. And so I'd like to start just by giving us an idea of the scale of our universe. I think this is one of the most amazing things, of course, about astronomy. What always baffles our mind right from the start is how large everything is. So I'd like to step through and give you some sense of how large everything is. So one thing we're going to see a lot of tonight will be the moon. Okay, and the moon is 400,000 kilometers away. This is a picture of the Earth taken from the surface of the moon. I'm going to show you these as much as I can, taken from the distant object, always looking back at Earth. And so you can see how quickly Earth gets small. So it takes light just over 1 second to reach us from the moon. It's been visited only 6 times by manned landings, and it takes a few days traveling at high speeds on the Apollo landers to get from here to the moon. Okay, so it's a long way away. It's been visited over 50 times. It's been tried to be visited over 70 times. Okay, many of them failed, and 6 manned landings. So the moon orbits around the Earth, of course, and that orbit isn't exactly a circle. Okay? As it orbits around the Earth, it goes through different phases as the sun shines on different parts of the moon. Okay? And because the orbit is not exactly a circle, sometimes it's a little bit closer to us and sometimes it's a little bit farther away. So this is a real time-lapse image of the moon as it goes through one full phase, one full orbit, and you can see that it gets a little bit closer to us, a little bit farther away. When it's closer, it looks a little bit bigger. Okay? And sometimes, okay, a few times a year, it will be at the point where it's closest to us, and it will also be in a full moon phase. So that's going to mean it'll be its brightest, and it'll be its largest, and therefore also brighter. Okay? So that's the worst time to look for a meteor shower, and that's what we have tonight. Okay. So the supermoon occurs at this point when it's at its closest approach and it's full. Okay? It's actually only about 8% larger than usual, okay? And it's about 16% brighter than usual. Okay? So it's not actually that much. You can't look at it, you're not going to look at it and say, wow, that's a supermoon. Okay? It just looks like the regular full moon. Unless you put them side by side, you can see one is a bit larger than the other. Okay? So it doesn't really matter, actually, that it's a supermoon. Anytime you have a full moon in the sky is not a great time to be doing this kind of astronomy. It's hard to see faint objects when the moon is up. Okay? But again, if we look away from the moon, and if we look before 10 o'clock when the moon rises, okay, then that's your best chance to see faint objects in the sky. So let's go a bit further out then. So that we said the moon was 400,000 kilometers away. Go out a bit further. This is Mars. Okay. Mars is 74 million kilometers away. It takes light 4 minutes. So if you turn on the lights on Mars, it'll take you 4 minutes before you see it light up on the sky here on Earth. Okay. This is a picture of Earth taken from the surface of Mars by one of these rovers that we've been sending up there lately. Okay, so you can just barely see it as a little speck. Mars is farther away from the sun than the Earth is. So if you're looking back at Earth, you're looking towards the sun. Okay. So you can only see the Earth either just before dawn or just after sunset. Okay, and so that's why the sky is bright, and you can see the Earth close to the sun as a little dot. Okay, and this is a blow-up of it, and it's just a little dot even from Mars, which is only 74 million kilometers away. Been 40 missions sent from Earth to Mars, but none of them, of course, have carried a person. The other planet I said you might catch a glimpse of is Saturn. This is Saturn. Okay, it's an hour and 15 minutes away for light to travel between Saturn and the Earth. Okay. This is a real picture of Saturn. So this is one of the 4 probes that we've sent to that planet, the Cassini probe. And here it is on the backside of Saturn. The sun is eclipsed by the planet. Okay, so the sun is on the other side. This glow that looks like it's CGI enhanced is not. What it is, it's the sunlight reflecting off the rings, and the rings glow and they light up the dark side of the planet. Okay, so it's actually the ring shine lighting up the planet. Again, this is actually a picture of Earth. Okay, so this was perfectly timed. Earth is there. There's a little dot seen between the rings. There's a blow up. You can actually, if you've got good eyes, and you can see from here, it's not quite a perfect dot. There's a little blob off to one side, which is the moon. Okay, so you can actually even just make out the moon from this picture. It's actually one of the things that's unusual about Earth, and we see is unusual the more planets we find. It's got but it has a very large moon. Okay, it's the only planet in the solar system that we know of that has a moon that is so large relative to the planet's size. Okay. That's where it is. The most distant planet from us is Neptune, okay, which you won't see with your naked eyes, no matter how dark the sky is here. And it takes like 4 hours to get from Neptune to us. Okay, and that's the most distant planet. We've only ever sent one probe to Neptune. So what you will see, in addition to Mars and Jupiter, a few meteors, will be some stars. The closest star to us, right, is not Alpha Centauri. Okay? Alpha Centauri is this guy here. Alpha Centauri is actually a binary system. There's actually 2 stars that you can't separate that make up Alpha Centauri. There's actually a 3rd star that we think also orbits around that pair. Okay? And it's actually at the moment closer to us than Alpha Centauri itself. This is called Proxima Centauri, and it's extremely faint, so you can't see it with the naked eye. But that's the closest star to us. It takes light 4.2 years to get from that star to us. This is 1 million times farther than Voyager 1 spacecraft has traveled so far. The Voyager 1 spacecraft is this thing that we've sent out of our solar system past Neptune. It's now gone past the main influence of the sun, of the sun's wind. Okay? But this is 1 million times farther away than that probe, which is the farthest we've ever sent anything out of the solar system. It's now going at a pretty good clip. But even if Voyager was pointed towards this star, which it is not, it would take it 74,000 years to get there. Okay. So it is very hard to get to even the closest star to us. So if we look up in the sky, we see a bunch of stars. There's about 2,000 stars that are within 50 light years of the sun. Okay, so relatively close by, but still a long way away, a long way for a space probe to travel, about 2,000 of them. Almost all the stars that you can see with your naked eye when you look up at the sky are a few hundred light years away. Okay, so you can look up, you see all those tens of thousands of stars in the sky, and they're actually all relatively close, a few hundred light years away. The reason I'm sort of emphasizing this is because there's a lot of excitement right now on looking for planets around many of these stars. Okay, so we now know of of almost 2,000 planets outside our own solar system that are orbiting these other stars that are relatively close by, but it would still take us a heck of a long time to ever get there. Okay? Or even to send a light signal back and forth would take 100 years. So here's a star with a solar system around it. This is one of the difficulties of doing these things. The star is quite bright. We're looking for planets that orbit quite close to that star. And you look in a big telescope and the star just washes everything out. So you have to do very clever techniques to try to reduce the glare of that star. And this is what's done in this picture. This was done by some Canadian astronomers a few years ago. This colorful stuff here is the noisy residual that's left after they do some corrections to get rid of that star. Okay, so this is just noise. And then these 3 red dots are the 3 planets that it detected. Actually directly observed these planets orbiting around the star. Most of these 2,000 planets aren't detected that way, okay, but a few of them have been, and more are all the time. In some cases, using techniques, we could even measure the chemical composition of their atmosphere. We can tell what kind of stuff the atmosphere around the planet is made up of. Okay? So this number is going up all the time. We're detecting planets around almost every star we look at. Okay? There's thousands and thousands of them. So this is very exciting for the prospects. You know, what we want to do, our goal right now, is to find a planet which is like the Earth, around a star which is like the Sun, and hopefully detect water in its atmosphere. Okay? This is a goal that I think we'll probably achieve within 20 or 30 years, if such a thing exists, okay, within the range that we can reach. So this will be an achievable goal. It's a step from there to actually detect life on these planets, but this alone would be an amazing thing to achieve, and I think that's around the corner. So all those stars that we can see, they seem to be spread evenly throughout the sky, okay, and they're all within about 100 light years. The one exception, if you have a dark sky, okay, and you look in this direction here, this is a scene from Ontario, you can see this more diffuse glow of light that stretches right across the sky, and this is the Milky Way. And this is billions of stars that are so far away you can't see the individual stars, you just see all their light added together as a band. And you also see that there's a dark patch through the middle of that light, and that's dust. It's like the smoke from your chimney, more or less, that is between us and those stars. The center of the galaxy is obscured by all that dust. And if that dust wasn't there, the center of our galaxy would be brighter than the full moon. Okay, even though it's a huge way away, I'm going to show in a moment how far away it is. It's extremely bright. All these billions of stars contain a lot of light, okay, but they're hidden by all this cosmic dust. If we look at the Milky Way in the southern hemisphere, we even see a couple of other faint blobs, which are other galaxies, even farther away, the large and small Magellanic Clouds. So all these stars we can see are part of a much larger system. Oh yeah, this is to say you will not see the Milky Way tonight for 2 reasons. One is this supermoon, the full moon, but also just the lights from Waterloo itself. You need to have a pretty dark sight to get a good look at the Milky Way. But so these stars we see are part of a much larger system, which is the Milky Way galaxy. The reason why it looks like a band across the sky is because it's actually a thin disk. Okay. This is looking at that disk face on. The sun is about here, 26,000 light years from the center of the galaxy. Okay. So that's what I mean when I said if you could see this bright bit at the center of the galaxy without any dust in between us and it would be brighter than the full moon. The sun goes around this whole thing once every 200 million years. And so the sun is about almost 5 billion years old, and so it's gone around the whole galaxy about 25 times. So there's several billion stars that make up this whole system. Loads of stars around them. Most of those stars will have planets around them. Okay? So there's tens, hundreds of billions of planets in our galaxy. And our galaxy is one of billions of galaxies. We're now looking at a map, a projection of the whole sky. Okay? This band through here is showing the Milky Way. This is our galaxy, which is close to us. And all these other dots, there's one colored dot for every galaxy in this picture. Okay? There's 100,000 galaxies in this picture over the whole sky. And these are relatively nearby galaxies. So the most distant one is about 2.7 billion light years away. Okay? That's about half the age of the Earth. So when the Earth was only about 2 billion years old, okay, that's the equivalent of, that's when the light we're seeing there was emitted by those stars. So what it means actually is by observing these galaxies, you're seeing the universe as it looked 2.7 billion years ago. Okay? And so we can actually trace how the universe has changed by looking back in time with these pictures. Okay. So this is pretty amazing. And so we know the distances to pretty good accuracy to millions of these, what I'm calling now nearby galaxies. You see, my definition of nearby keeps changing with every slide. So I'm now going to say that these things that are 2.7 billion light years away are nearby galaxies. Right? The most distant galaxies we know of come from, mostly from this picture. This is a deep picture taken by the Hubble Space Telescope. It stared in one spot in the sky for about 2 months. Okay, just kept the shutter open and took this exquisite picture. Unlike, so this looks like a bunch of stars, like you might see when you look up at the night sky. Almost everything in this picture is not a star. Okay? That's a star, that's a star, and that's a star. That's about it. Everything else there is a galaxy consisting of about 10 billion stars. Okay? They chose where to point the Hubble Space Telescope because they said, let's look somewhere where we don't see anything. Let's point at a blank piece of sky. Okay? Open the shutter, and you see thousands and thousands of these distant galaxies. Most of them are about 10 billion light years away. And the most distant objects are about 12 billion light years away. The universe is only 13.5 billion years old. So the things that are most distant there, we're looking at them, we're seeing the universe at a moment just after it formed. Okay? So by looking at pictures like this, we can reconstruct the whole history of star formation and galaxy formation throughout the history of the universe. So that was to give you this crazy rapid walkthrough of how big everything is. Now I want to come back a little closer to home again and talk about things in the solar system. And talk about what is a meteor, these things that we want to maybe see tonight. Okay. So here's a picture of a meteor. Okay, what you see is you see a brief flash of light that streaks across the sky. Usually does not last very long, so it won't go all the way across the sky. It lasts for a little bit and then disappears. Okay? And they just last for a fraction of a second, most of them. Okay? Some of them are bright and some of them are faint. Okay? You can see meteors any night of the year. Almost if you have a dark sight especially and you just look up, let your eyes get dark adjusted, you can see meteors all the time. They're caused by little bits of rock and dust that the Earth passes through on its orbit around the sun. Okay? And although space is really quite empty, there's lots of little bits of rock and dust up there. And so the Earth is always passing through these little bits of stuff. And as they burn up in the atmosphere, they create these little meteor trails. So the meteor shower happens when the Earth passes through some region of space where there's a lot of this dust and rock. Okay? And so this is an image of a meteor shower, a time-lapse image where we're seeing, so you don't ever see this many at once. Okay, this is probably over about a course of an hour or two. Okay. So you see all these individual flashes. You can see how they seem to come from about one point in the sky, okay, but then they spread out across the sky. For the most part, and certainly for the Perseid meteor shower, all the bits of rock that cause these flashes of light are tiny specks of dust. Okay? So none of these things are going to hit the ground. They're not going to hit you on the head. They're not going to burn up as a giant fireball in the sky. They're little bits of dust, microscopic dust in many cases, that burn up in the atmosphere. They're moving so quickly, they create a bright flame. At their peak, you can see about 100 Perseid meteors per hour. It will be hard to see that many with the full moon, but you will see the brighter ones. Okay. And there are several of these meteor showers, some that give you lots and some that give you a few. I like this picture. This is a picture of the Perseid meteor shower taken from the International Space Station. Okay, so this is the space station here. Someone's up here with a camera. They're looking down at Earth, and this streak here, this is a Perseid meteor going down towards the Earth, and so you can see it hitting the top of the atmosphere there. Okay, so it was the first ever Perseid meteor seen looking from above rather than looking from below. So now it sounds like I'm going to switch gears. I want to talk about comets, okay? Because I'm going to show that comets are closely linked to meteor showers. Okay? So comets are these spectacular objects that we see occasionally in the sky. They're not always there. Okay? So here's a comet. This is Halleys Comet. They look different from all other things that we can see in the solar system. They have these bright, fuzzy heads, or comas, and they have these long tails, two of them. Okay? There's a curvy orange tail and a straighter blue tail. The tails extend for millions of kilometers. They always point away from the sun, no matter which direction the comet is moving. The other thing is that comets don't always look the same. Okay? So if you look in some piece of the sky, you see nothing, and all of a sudden one of these things lights up, and it looks like a comet. And then it disappears again sometime later, okay? Depending on the orbit, days later or months later. So this, of course, caused lots of consternation in past days when we didn't know what comets were. You look up in the sky, it's always looked the same, and all of a sudden there's one of these crazy things hanging there in the sky, and it just hangs in the sky for about a month, and then it just disappears. Okay? And so that can make you very nervous when you don't know what it is. Okay? But now you have a pretty good idea what they are. Right? They're basically asteroids. Okay? So asteroids are these big chunks of rock that float around in space. Some of them come close to the Earth. Most of them are in the asteroid belt between Mars and Jupiter. Okay? But for some reason, some of these asteroid-like things, when they get close to the sun or they get close to the Earth, they light up like a comet. Okay? This is a picture of the core of Halleys Comet, okay, that was visited a couple of decades ago now. I'll talk about that more later. Okay? So it looks like an asteroid. It's a big chunk of rock, okay? But it's outgassing. Okay? It's giving off vapor and dust and gas, not all over the place, but in certain directions. Okay? And it's this gas and dust that creates these tails. Okay? Asteroids don't do this. Comets do. That's the only difference. Okay? I'll say in a moment why that is. So what's the relation between comets and meteor showers? Well, as a comet comes close to the Earth, and therefore close to the sun, the heat from the sun causes any water ice, and also more exotic things like methane ice and ammonia ice. It causes them to vaporize, and that causes these vents of gas to explode and expel dust and little particles, okay, from the comet. And so it leaves behind a little trail of debris. Leaves behind a trail of debris as it goes around the sun. And every time it goes around the sun, it loses some bunch of small particles. They spread out along the orbit. The comet goes back where it came from and then revisits sometime later. What happens is if one of these chunks of debris happens to lie in a place where the Earth passes through it, okay, as it goes on its orbit around the sun, then you get a shower of these particles, and that's the meteor shower. So almost all these famous meteor showers that we know are basically the remnants of a comet that once passed by the sun and left behind a debris of particles. The Earth now passes through that, and we see them as these spectacular meteor showers. So we can generally actually now identify for a given meteor shower which comet they came from. And as early as 1866, it was observed that the orbit of the Perseid meteors that we see correspond to this comet shown there, the comet Swift-Tuttle. They predicted when that comet would return. I think it was 1986. It didn't return in 1986, and people scratched their heads, redid their calculations, re-predicted that it would show up in 1992, and then it did. Okay? It's extremely hard to predict the orbit of a comet, partly because every time it passes through the sun, it goes through this fairly explosive event where it loses a lot of its mass in jets that go in different directions. Okay? And it can be hard to model and hard to predict what that does to the orbit. Okay? So even though you can do your calculations right, it can be hard to predict when it's going to come back again, especially when there's such a big difference between 1866 and 1992. Okay? But the predictions were right, and so we now identify that that comet was the source of the Perseid meteors. It will next come by in 2126. I should be retired by then, I hope. The Perseid, the Swift-Tuttle comet actually comes by pretty close to the Earth. Okay? And in the year 4500 almost, it should come pretty close to the Earth, about 5 million kilometers away. Okay, so that's, it's not really a cause for concern in any sense, but of course, when we fold in the fact that, that we can't predict these orbits exactly, there's room for error on that number. Okay? But I'm not worried about this. There's loads of stuff out there that could hit us, that will hit us before Swift-Tuttle, so I'm not worried about Swift-Tuttle. Okay. So where do comets come from? So the idea is that this is some asteroid-like body that has a lot of ice on it, okay, and that ice then gets heated up by the sun. So the ice tells us something about where it came from. If you stand in space and you face the sun, and you rotate a little bit maybe, in orbit around the Earth, the temperature is about 5 degrees. Okay, it's not actually that cold. Right? But if you go a little bit farther away from the Earth, it quickly gets colder. By the time you get to Mars, it's minus 56 degrees. So Earth is just at the right place around the sun where water can be a liquid and a gas, okay, quite comfortably. So if you have ice that's farther away from the Earth and then it gets close to the Earth, it will heat up to the point where it can become a gas, and that's what's happening to these comets. When the solar system formed 5 billion years ago, okay, it was actually a lot hotter. We're pretty sure it was more than 300 degrees Celsius, okay, at the position of the Earth. So this means that actually any ice that was existing within the orbit of Jupiter today would have turned into a gas long ago and been lost. So actually, if you look at the asteroid belt between Mars and Jupiter, there's no ice there, okay? Even though it's cold, because all that ice was lost when the solar system formed. So the only place that ice could be coming from is even farther away. And so we now know that these comets that bring this ice towards the Earth originate from beyond the orbit of Neptune. So there's a model of the solar system in the upper right. Okay, we're now looking, so you can't even see Earth and Mars. They're quite close to the sun on there. You can see the orbit of Jupiter, Saturn, Uranus, and Neptune. And beyond Neptune now, we know there's all these, basically another asteroid belt of small rocky bodies. We now know that Pluto, in fact, is one of these small rocky bodies. One of just thousands, tens of thousands of objects just beyond Neptune. So this is part of what we call the Kuiper belt, which we believe extends out to about 2.3 light days from the Earth, and creates this vast belt of rocks which contain ice, okay? And what that means is that they're basically untouched from when the solar system formed. Okay? They've never been in closer than they are now, because if they were, that ice would have melted, okay? and we wouldn't see, and it wouldn't be there now. So this is a pristine record of what the solar system looked like before it formed. So extremely valuable to us to learn about what the conditions were like before the Earth formed. And that's where comets come from. That's where some comets come from. Some of them come from even farther away. Okay. Some of them come from what we think is called, well, what we call the Oort cloud. Okay. We've not observed the Oort cloud directly. It's extremely far away, and it's made up of small objects. Okay. Comets are basically small objects. Okay. We think it contains trillions of comets, and they surround the Earth. Sorry, they surround the sun. Okay. And they extend out to a distance of about 1.5 light years, basically halfway between us and the next star. Okay. Because anything that was farther away than that would be orbiting around the next star instead of us. Okay. So again, this is a huge record of trillions of comets that hold the clues to what the solar system looked like when it formed. So comets are of great interest scientifically for that reason. We can study them from the ground, but it's even more exciting to go and visit them directly. Okay? It's very hard to do because comets are on orbits that are very different from the Earth's orbit. And traveling around in space is quite a difficult thing to do. So if you've seen the movie Gravity, you know that all you have to do if you want to get from point A to point B in space is you just point your ship there and you hit the gas and you go. And actually, if you do that, you won't go anywhere like you want to go in space. Traveling in orbit is a difficult thing to do. I'm going to show you a cool little animation in a moment. Okay? And so, for example, when we wanted to visit Halleys Comet, the velocity of Halleys Comet relative to the Earth is 70 kilometers per second. Okay? It's very hard to get your spacecraft to match that speed. Okay? And so you end up, what happened was the Giotto probe whizzed by that comet at high speed. It was a dangerous thing to do because this thing is throwing off little bits of dust and rock, right, as we talked about. And even though there's small pieces of dust and rock, if I throw a small rock at your head at 70 kilometers per second, it hurts. And if you throw it at your space probe, it hurts the space probe. Okay? And it did hurt the space probe. It caused it some problems, but it recovered. And it took this nice picture of the core of Halleys Comet. We were surprised to find it's actually extremely dark. It only reflects 4% of light. It's darker than the asphalt on your driveway, okay? Which was kind of a surprise for something which is thought to be a block of ice. Okay? And the ice vapor, that is the water vapor that is escaping, is not escaping from all over the asteroid or the comet. It's escaping in jets, where we can see the bright spots just on one side. Okay? So comets seem to be covered with this tar-like dark material, okay? And the jets that cause the coma and the tail just come out from about 10% of the surface. So that was quite neat to see. Since then, we visited a few comets. All of these four have been the same thing. They've been these flybys at rapid velocity. Okay, so there's Halleys Comet in '86. Comet Wild was the one that they collected some of the dust that was being outgassed from the comet and brought it back to Earth. The Comet Temple, the Deep Impact, this was the one that they crashed a space probe into on the 4th of July for some reason. Okay. The mission that is going now, and you may have heard about in the news, it's really super cool. Actually, I'd only heard of this. Again, comets are not really my specialty. There's a probe called Rosetta, and it's been on a 10-year mission to visit one of these comets. Okay? The reason why it's been a 10-year mission is because it wants to not just fly past this thing, but it actually wants to get close to it so they can take pictures of it for a long time. It wants to not only do that, it wants to go into orbit around this thing, which is very, very hard to do. It wants to do not only that, it wants to land on the comet, okay, and actually take samples from the comet. To do that, you've got to make the orbit of your space probe match the orbit of the comet, and that's a very difficult thing to do. So let me see if this works. So this is an animation on the European Space Agency website. Okay, what you're seeing here, this is the solar system. Sorry, my pointer, or Nash's pointer has died, so I'll just hand it back. So there's Earth. Oh, jeez. Okay, yeah, okay, that's great. Yeah, that's why it's so good. Okay, so this is Earth here, and this red line, this shows the Rosetta space probe being launched from the surface of the Earth 10 years ago. This is the comet that it wants to reach. Okay, it's Comet 67P. So we follow that a little bit. Okay, you can see the orbit of the comet, the orbit of the comet is completely different from the orbit of the Earth. Okay, so we launch the space probe like this. It does a bunch of crazy things. It's going to fly by the Earth again. I think that's what it does first, or perhaps it's Mars. Okay, so there's the space probe. Okay. That's a flyby of Mars. It comes back towards the Earth, uses the Earth's gravity to give it another kick. That launches it into an even higher orbit. Here's the comet coming back into view. Okay. Now you're getting close to matching the orbit, and now it's got to chase and catch up to this comet. It's going to need another kick. Again, it comes back to the Earth, gets another kick from the Earth. Right. They have to plan this thing. It's amazing. I mean, They have to have smart people. And this wasn't this wasn't the initial goal. Initially, they're going to go after some other comet, and the mission got delayed. So they planned some crazy thing like this, and then the mission got delayed, and then you can't just start this over again on a different day, right? You have to know what you're doing. And so they said, well, let's go after this different comet again. They had to redo all the calculations and come up with this rather elaborate trajectory. Should come back into view in a moment. Okay. There we can see it around where it is today. This has been the excitement over the past few months. The space probe just catching up with the comet. It arrived there a few days ago, safe and sound. It's now orbiting around that comet at a slow speed of about 1 meter per second. Right? Okay. And it's going to travel around it, and it's going to send a little lander down and land on the comet. So this is, I won't run it again unless there's more time, but this is great. If you just look for the Rosetta website on the European Space Agency, you can get this little 3D animation. It's quite cool. But so it's not an easy thing to do. Right. So from computer models, we had a pretty good idea what this comet looked like before we went there, and that's what the computer models predicted that the nucleus would look like. Now we're there and took a picture. That's what it looks like. Okay? So it looks nothing like the computer models. Okay? It's a pretty crazy looking thing. It's got a density lower, about a factor of 10 lower than the density of water, but it's made up of rock and ice. But so it can't just be some solid chunk. It's got to be just a bit of loosely held together gravel. So this is, first of all, quite cool. And secondly, it's a bit challenging because they want to land on this thing. Okay, so where do you choose to land? So they're now looking for places to land, and they're finding places that look kind of promising like this, but as they look closer and closer, you see these large boulders. This is still from 100 kilometers up in the sky above the comet, so these are huge boulders.
Is that UW, isn't there?
Yeah, that's right. Yeah, that's true. Yeah, UW. Yeah, that's awesome. Yeah, okay. Cool. Okay. Okay. So it's a pretty low mass. It's a low density thing. It's about 4 kilometers across. It's got the same mass as a piece of rock that was 1 kilometer across. Okay, that's a pretty big and heavy rock. But now still, to think about to go into orbit around that thing, right? You're using the gravity of this giant rock to go into orbit around. It's quite amazing they can do this. So this is the real picture of the comet as it is now. This is the plan: is to launch this little lander, which is going to land on the comet, dig up soil samples, and tell us lots of things. What is it going to tell us? Well, it'll tell us, first of all, so we've learned something about the shape. It'll tell us what the comet is made of. What is this black tar that covers the surface? We think it might be organic compounds, okay, and that's quite interesting. There's a lot of theories and ideas that comets may have been responsible or helpful in seeding life on Earth. Okay? It turns out that in some experiments, it looks like it's easier to make things like amino acids and dipeptides, which are complex molecules needed to form life. It's easier to make these things in the conditions of space than it is on Earth. Okay? Even in prehistoric Earth, when conditions were very different from what they are today. We know there's amino acids on comets. Okay? We don't know if there's dipeptides. Right? We're now going to have a close look at all these organic molecules on the surface of this comet and learn what kind of things might be out there, hanging out there in the Oort cloud far beyond Neptune, okay, representing what the solar system used to look like. And could they have been responsible for bringing these seeds of life to Earth when Earth formed? So it's possible. So most of the stuff that we can see around Earth now, it's been massaged by the solar system for 5 billion years. It's been heated, stirred, compressed, chemically modified. It's been changed. It no longer looks like what things looked like before the Earth formed. So the stuff in this Kuiper belt in the Oort cloud that are far beyond the orbit of Neptune, they've basically been in this deep freeze hibernation ever since the solar system formed. Right? And so they hold these clues of what might have been there at the time that the Earth formed. They're extremely faint, they're extremely small, and so it's hard to study them from Earth with current telescopes. The next generation of telescopes that are being built now have 30-meter aperture mirrors. That doesn't mean a lot to most of you, but that's huge. Okay? That makes them up to 100 times more powerful than any telescope we have on Earth now. And they will be able to tell us the chemical compositions of hundreds or thousands of these things, amongst other things. So I'm very angry with NIES because he didn't mention the most exciting telescope that is being built and is being...
I left it for you.
Yeah, exactly. So this is going to be the 30-meter telescope. It's going to begin construction in Hawaii this fall. This is looking down on the mirror. So the mirror is made up of about 500 individual mirrors. Each of these segments is about this big, okay, huge. On the back of each one of those segments is a whole bunch of mechanical actuators which can deform the shape of the mirror. Okay? So all those 500 segments are all adjustable in their shape on fractions of a second time scale. So they take out all the fluctuations in the Earth's atmosphere. They take out all the twinkling that you see in the stars, and they give you super sharp images. That requires a very sophisticated system involving a huge laser, okay, that is Canadian designed. So the dome here, which is also a key part of the success, is a Canadian designed dome. And the system that causes all the mirrors to shake and deform and take out the atmospheric effects is the Canadian designed system. Altogether, these 500 segments make up a 30-meter diameter aperture telescope, which makes it 100 times more powerful than anything we have on Earth today. So we're very excited about this. I'm going to show you just a few sort of pictures of things that you can do with this giant telescope compared to what we can do today. So we've been talking about solar system. This is a picture of one of the moons around Jupiter, Io. This is this really cool volcanic moon. Okay. We have great pictures because we sent a space probe that went right next to it and took some pictures. Okay. That's extremely expensive to do. This is the best picture we can take of it from the ground today. And this is the picture we will get with the 30-meter telescope. We can see volcanoes. We can see geysers erupting. We can now, instead of just sending some space probe and see what it looks like on that day, we can watch it day after day, and we can see these things. We can see rainfall on Titan. We can see geysers on Enceladus. We can see volcanoes on Io. This is that picture I showed you earlier of the most distant galaxies we've ever seen, taken by the Hubble Space Telescope, staring at one region of the sky for 2 months. This is a small piece of that large picture. Okay? We zoom into the galaxy. This is the real picture from the Hubble Space Telescope. It's amazing. This galaxy is on the other side of the universe. Right? It's one of the first objects to form. This is what it will look like with our 30-meter telescope. Right? As clear as the pictures of things we see right near us today. We can look at the chemicals that make up this galaxy. We can look at these dust lanes. We can distinguish the stars that are in the center region from the stars that are around it. We can learn a lot about how all these galaxies formed over the last 13 billion years. And that's just a small slice of all the things this telescope is going to do. It's an extremely exciting project. Construction starts this year in Hawaii, the best observing site, at least in the northern hemisphere. Canada's been a partner in the design from the beginning of the project. About 15 years ago is when the project started. We designed the dome, and we designed this mirror thingy system. Okay? We hope to be able to participate in construction and science operation. We need a lot of money, and we need it by the spring. Otherwise, we will not be in this project, and we will lose all the investment we've made in those things. But I don't want to be negative. It's going to happen. We're good. But this will be the next major astronomical facility on the planet, and we really hope that we're going to be a part of it. And there's a lot of astronomers here at Waterloo that are anxious to use this and be involved in all the science teams and planning that have been going on and will continue to go on. Okay, so that's a lot of stuff. I told you I was going to fly through a lot of things. That's all I want to say. So I'm done. I think Heather's going to talk about logistics now. Okay, so thanks.